Foundation of data systems. First full chapter go through the fundamentals ideas that apply to all data systems, whether, whether running on a single machine or distributed across a cluster of machines. Chapter 1 introduce the terminology and approach that we are going to use through this book. It examines what we actually mean by words like reliability, scalability, and maintainability, and how we can try to achieve these goals. Chapter 2 compares several different data models and query languages. The most visible distinguishing factor between databases from a developer point of view. We will see how different models are appropriate to different situations. In Chapter 3, turns to the internal of storage engine and looks at how databases lay out data on disk. Different storage engines are optimized for different workloads, and choosing the right one can have a huge effect on performance. Chapter 4 compares various formats for data encoding, serialization, and especially examines how they fare in an environment where applications requirements change and schemas need to adapt over time. Later, part 2, we turn to the particular issue of distributed data systems. Reliability, scalability, maintainability. Reliability, tolerating hardware and software faults and human error. Scalability, measuring load and performance, latency, percentiles, throughput. Maintainability, operability, simplicity, and evolvability. Chapter 1 Reliable, Scalable, and Maintainable Application. The internet was done so well that most people think of it as a natural resource like the Pacific Ocean, rather than something that was man made. When was the last time technology with a scale like that was so error free? Alan Kay in an interview with Dr. Doug, Journal 2012. Many applications today are data intensive, opposed to compute intensive. Raw CPU power is rarely a limiting factor for these applications. Bigger problems are usually the amount of data, complexity of data, and the speed at which it is changing. That intensive application typically built from standard building block provide commonly needed functionality. Example, many application needs to store data so that they or another application can find it again later. Databases. Remember the result of an expensive operation to speed up reads, caches. Allow users to search data by keywords or filters it in various ways. Search indexes. Send a message to another process to be handled asynchronously. Stream processing. Periodically crunch a large amount of accumulated data. Batch processing. If that sounds painful, obvious, that's just because the data systems are such a successful abstraction. We use them all the time without thinking too much. When building an application, most engineers wouldn't dream of writing a new data storage engine from scratch because databases are a perfectly good tool for the job. But reality is not that simple. There are many database systems with different characteristics because different applications have different requirements. There are various approaches to catching, several ways of building search indexes, and so on. When building an application, we still need to figure out which tools and which approaches are the most appropriate for the task at hand. And it can be hard to combine tools when you need to do something that a single tool cannot do. Done. This book is a journey through both the principle and the practicalities of data systems and how you can use them to build data-intensive applications. We will explore what different tools have in common, what distinguishes them, and how they achieve their characteristics. In this chapter, we will start by exploring the fundamentals of what we are trying to achieve. Reliable, scalable, and maintainable data system. We'll clarify what those things mean, outline some way of thinking about them, and go over the basics that we will need for later chapter. In the following chapter, we will continue layer by layer, looking at different design decisions that need to be considered when working on a data intensive application. Thinking about data systems. We typically think of databases, queues, caches, etc., as being very different categories of tools. Although a database and a message queue have some superficial similarity, both store data from some time, have very different access patterns, which means different performance characteristics, and thus very different implementation. So why do we lump them all together under an umbrella term like data systems? Many new tools for data storage and processing have emerged in recent years. They are optimized for a variety of different use cases, and they no longer neatly fit into traditional categories. For example, there are data stores that are also used as a message queue, Redis, and there are message queue like with databases like Durability, Guarantee, Apache Kafka. The boundaries between these categories are becoming blurred. Secondly, increasingly, many applications now have such demanding or wide-ranging requirements that a single tool can no longer meet all of its data processing and storage needs. Instead, the work is broken down into tasks that can be performed efficiently on a single tool, and those different tools are stitched together using application code. For example, if you have an application managed caching layer using Memcache or similar, or a full text search server such as Elasticsearch or SOAR, separate from your main database, it is normal the application code responsibility to keep those caches and indexes in sync with the main database. Figure 1/1 give a glimpse of what this may look like. We will go into details in later chapter. Figures 1/1, one possible architecture for a data system that combines several components. When you combine several tools in order to provide a service, the service interface or application programming interface API usually hides those implementation details from clients. Now you have essentially created a new special purpose data system for a smaller general purpose component. Your composite data system may provide certain guarantees. Example, that the cache will correctly invalidate or update it on writes so that outside clients see consistent results. You are now not only an application developer, but also data system designer. If you are designing a data system or a service, a lot of tricky questions arise. How do you ensure what the data remains correct and complete, even when things go wrong internally? How do you provide consistently good performance to clients, even when part of your system are degraded? How do you scale to handle an increasing load? What does a good API for the service look like? There are many factors that may influence the design of the data system, including the skills, experience of the people involved, legacy system dependencies, time scale for delivery, the organization tolerance of different kind of risk, regulatory constraints. Those factors depend very much on the situation. In this book, we focus on three concerns that are important in most software systems. Reliability. The system should continue to work correctly, performing the correct function at the desired level of performance, even in the face of adversity, hardware, software, faults, and even human errors. Key reliability on page C. Scalability. As the system grows in data volume, traffic volume, or complexity, there should be reasonable ways of dealing with that growth. See scalability on page 10. Maintainability. Over time, many different people will work on the system, engineers and operation, both maintaining current behavior and adapting the system to new use cases, and they should all be able to work on it productively. See maintainability on page 18. These words are often cast around without a clear understanding of what they mean. In the interest of thoughtful engineering, we will spend the rest of this chart exploring way of thinking about reliability, scalability, and maintainability. And In the following chapters, we will look at various techniques, architectures, and algorithms that are used in order to achieve these goals. Reliability. Everybody has an intuitive idea of what it means for something to be reliable or unreliable. For software, typical expectation includes the application performs function that the user expected. It can tolerate the user making mistakes or using the software in unexpected ways. Its performance is good enough for the required use case under the expected load and data volume. The system prevent any unauthorized access and abuse. If all those things together mean working correctly, then we can understand reliability as meaning probably continuing to work correctly even when things go wrong. The things that can go wrong are called faults. Called faults. Systems that anticipate faults and can cope with them are called fault tolerant or resilient. Former term is slightly misleading. It suggests that we could make a system tolerant of every kind of fault, which in reality is not feasible. If the entire planet Earth and most everything on it were swallowed by a black hole, tolerance of that fault would require web hosting in space. Good luck getting that budget item approved. So it only makes sense to talk about tolerating certain types of faults. Note that a fault is not the same as a failure. Fault is usually defined as one component of system deviating from its spec, whereas failure is when the system as a whole stops providing the required services to the user. It is impossible to reduce the probability of a fault to zero. Therefore, it is usually best to design fault-tolerant mechanisms that prevent fault from causing failures. In this book, we cover several techniques for building reliable systems from unreliable parts. Counterintuitively, in such fault-tolerant systems, it can make sense to increase the rate of faults by triggering them deliberately. For example, by randomly killing individual processes without warning. Many critical bugs are actually due to poor error handling. By deliberately inducing faults, you ensure that the fault-tolerant machinery is continually exercised and tested, which can increase your confidence that faults will be handled correctly when they occur naturally. The Netflix Chaos Monkey is an example of this approach. Although we generally prefer tolerating faults over preventing faults, there are cases where prevention is better than cure because no cure exists. This is the case with security matters. Example, an attacker has compromised a system and gained access to sensitive data. That event cannot be undone. However, this book mostly deals with the kinds of faults that can be cured, as described in the following section. Hardware faults. When we think of causes of system failure, hardware faults quickly come to mind. Hard disk crash, RAMs become faulty, power grid has a blackout, someone unplugs the wrong network cable. Anyone who has worked with large data centers can tell you that these things happen all the time when you have a lot of machines. Hard disks are reported as having a mean time to failure (MTTF) of about 10 to 15 years. Thus, on a storage cluster with 10,000 disks, we should expect on average one disk to die per day. Our first response is usually to add redundancy to the individual hardware components in order to reduce the failure rate of the system. This disk may be set up in a RAID configuration. Server may have dual power supply and host swappable CPUs, and data centers may have batteries and diesel generation for backup power. When one component dies, the redundant components can take its place while the broken component is replaced. This approach cannot completely prevent hardware problems from causing failures, but it's well understood and can often keep the machine running uninterrupted for years. Until recently, redundancy of hardware components was sufficient for most applications, since it makes total failure of a single machine fairly rare. As long as you can restore a backup onto a new machine fairly quickly, the downtime in case of failure is not catastrophic in most applications. Thus, multi-machine redundancy was only required by a small number of applications for which high availability was absolutely essential. However, as data volume and application computing demand have increased, more applications have begun using large number of machines, which proportionally increase rate of hardware faults. Moreover, in some cloud platforms such as Amazon Web Services (AWS), it is fairly common for virtual machine instances to become unavailable without warning, as the platforms are designed to prioritize flexibility and elasticity over single machine reliability. Hence, there is a move toward systems that can tolerate the loss of the entire machines by using software fault tolerance technique in preference or in addition to hardware redundancy. Such systems also have operational advantages. A single server system requires planned downtime if you need to reboot the machine to apply operating system security patches, for example. Whereas a system that can tolerate machine failure can be patched one node at a time without downtime of the entire system. A rolling upgrade. See Chapter 4.